Let's go through an example of a related rates problem. Um, let's say that there's a deep a deep pyramid-shaped pool, and it's getting filled with water. Let me get a picture to help you see that. All right, I'm drawing my square top, um, slanted to give that 3D effect. And let's say it's pretty sharply deep, right? So there's the front of the square going down like that, and there's the right side of the square going down like that. And I'll draw this to give you that feeling of the backside going down to the point, but I'm not gonna fill it in. I want that 3D feel to be emphasized by that not being continued on the other side where you can't see it because the front's blocking it. So I'll type a few words. Pyra, pyramidal pool being filled up at a rate of, I don't care, 10 cubic units per second. I mean, I could just say per time, right? Time unit, but I'll say second. I don't really care about the units. Could be cubic feet, cubic meters, cubic miles. Doesn't really matter. So I'll just leave that cubic units per se, but I'll do per second so we have a concrete time unit to think about. So that means we've got water pouring in at a pretty decent rate. Going in there, and then 10 cubic units per second in. That's what the down arrows are about. So they've given you a rate. That's not very surprising because this is a related rates question. If the question is not labeled related rates, this idea of being given a rate might make you start thinking, oh, maybe this is a related rates question. One of the key issues in a related rates question is that we've got different variables changing over time. So think about this. We've got S, that's the side of the square. It's S by S, right? And we've also got how deep the water is. So I'm just going to draw some generic water about halfway full. Picture not to scale. And I'm going to shade down below the water to really give that indication of, hey, there's water down there. You know, I should probably have done something clever like made those lines blue. It might be a little too late to do that, but let me just try, see what happens. Thicker and blue. I don't want to make too big a deal about this, but it'll be kind of nice. All right, a little bit of blue helping you see the rate of water going in and that we're at a certain depth. So, well, we got to talk about volume. Cubic units means we need volume. And of course, we know the generic formula, or we're given the generic formula for the volume of a pyramid. The volume of a pyramid is 1/3 of the base area. So I'm just going to put that in as S squared, right? The volume of the base area times the height. Okay, so there's that. Sometimes, I won't say usually, but sometimes there's an extra fact, such as this pool is 3 times deeper than it is wide. Well, what does that mean? Well, that means that this total height is 3s. By the way, do you notice how generously I'm using my diagram? You might want to transfer the picture on your screen, if any, to your whiteboard and start marking it up. There's too much information to keep in my head all at once. And then the final fact, the final question, the final related rates question. How fast is the width of the water's surface changing when it is 15 units deep? Finally, we get a question. How fast is, right? And you're like, oh, good, this is related rates. They started with giving us a rate, and they wound up asking about another rate. How fast is something changing, right? How fast is the width of the water's surface changing? They want ds dt, right? S is defined as the width, so they want ds dt. When the pool is 15 units deep, so that's h equals 15, right? They are giving us h equals 15. And they're asking, what is ds dt? And of course, I did forget one thing. When we define V as the volume, we ought to have noted the fact that dV dt equals 10. All right, so we have fact one given to us in the first sentence, the formula given to us. The pool is 3 times deeper than it's wide. That's another fact. And then finally, a question. They're asking for ds dt, but they're giving h as 15. The pool is 3 times deeper than it is wide, right? That was the 3s. So I could also represent that by h equals 3s. That's really what I did, is I just replaced h with 3s, because the height, the depth, it really is 3 times more than the width. So I have a lot of references, a lot of formulas that I know, facts that I'm given, and a single question. Well, if you look at the volume formula, there's no dV/dt to plug the 10 into. There's no ds/dt to find, right? So what you've got to do is you've got to make sure to find the related rates. Take the time derivative of everything. Now, of course, that'd be kind of nasty if we kept s squared and h separate. We'd have to do the product rule. But nicely, they related h to 3s. So one of the first questions you might be asked is simply restate the volume in terms of a single variable. That just means substitute away either the s or the h. And because I see that h is linear, I'm simply going to substitute away the h. If that didn't show up on my multiple choice, I would try letting s equals h over 3 and substituting it in there, right? Either way, I can substitute away one variable because this is always true. So when I put in the h, when I substitute away the h by putting 3s in for h, I'm not going to make a big deal of it, right? The 3 and the 3 cancel. This is times 3. That's divided by 3 over here. And for the s, well, I have s squared over here, so I get s cubed, right? So the first thing I do is I create the simplified related volume formula. This is it. There's just s cubed left over. There's nothing else. Kind of nice. No pi's floating around, no 7s, no 1/3. Doesn't matter if there were those, they're just constants. Don't get flummoxed by nasty looking constants. V equals s cubed. That's all there's left. Now, right, PS, H is 3s. So when the height is 15, I know S is 5, right? The height's 3 times bigger than, right? So do I put in S equals 5 right now, right? Should I do that right now? Put in S equals 5? Well, no, of course not. Because you put in 5, you would just get 125. And when you tried to take the derivative, it'd be a constant at 0. Remember, S is changing over time as you pour in water, right? The width of that top of the pool changes. So you can never substitute it in early. H equals 3s, that remains true even over time, right? That pyramidal relationship of height to width remains true all the time. So you can substitute it in anytime you want. Well, now I've got v equals s cubed, so clearly what I need to do is take the time derivative of both sides. So the time derivative of volume is very easy. You just get dv dt. And the derivative of s cubed is quite easy also. It's 3 s squared, and then of course it's ds dt. Remember, this wasn't an s derivative where we wouldn't have an extra term. This was a t derivative. S changes with t, so it's a function of t. So the chain rule applies. We need a chain term because of the s, and that's ds dt. Now we're doing well. Now we have the equation where we can indeed substitute in everything. At this stage, we can. At this stage, we can put in the 10 and put in the 5 and solve the ds dt, right? If you want, you can do all the algebra first. ds dt equals dv dt over 3s squared, right? Get all the algebra done first and then substitute in. But in this case, I think it'll be simple enough to put in the 10 and the 5, right? So this transforms itself into the equation 10 equals 3 times 25, right? I'm not going to write down 5 squared. I'll just 3 times 25 over here. And ds dt, right? That's the thing I'm looking for. And I don't think it's too hard for you to see ds dt equals 10 over 75, which we can swiftly reduce to 2 over 15. Now, I made these numbers up on the fly. If I had premeditated things a little bit more, I might have modified the 10, so this came out an integer. On the other hand, a simple rational fraction is quite legitimate in terms of a test-like item. The process was the important part. Recognize you've been given a rate, or there's two things changing in your diagram. Volume and height and width are all changing with time. So things are complex, but wait a second, they're giving me an algebraic relationship between two variables, so I can substitute one away. Then you can take your very your very nice derivative because you've only got one variable. Careful with your constants, careful with your derivatives. And at that point, you're ready to substitute in all the numerical values that you have. Not earlier, only algebraic relationships should be substituted in early. So substitute algebra first, take the time derivative, substitute in the numbers you know for all the variables, and solve for the one that you're being asked about. That's all it is for just about any related rates problem. I hope this helped. I hope this helped you think about how this works as a process, and I would ask you to go practice that process on, the examples in the textbook or even the diagnostics in the textbook to make sure that you follow this process, right? Simplify using a given variable relationship, take the time derivative so we have related rates, and then substitute in all the numerical values that we have been given, right? Last step is numerical values. And do careful algebra to solve for the variable they're interested in. As a final note, of course, you do see that there are 3 variables in this related rates equation. So in this case, you were given the S and given the dV/dt and asked for the ds dt. You could have been given the S and the ds dt and been asked what the dV/dt was. Or you could have even been given the 2 rates and asked, hey, how wide is the square at that moment? So don't be too concerned if you're asked a slightly different question. It's still going to be the same process. They'll be giving you a constant and they'll be giving you a relationship, and all you got to do is simplify, do your time derivative, substitute in everything you've been given.